Hello, it's Richard Hammack's Calculus 1. We are in part 5 of the course on integration. This is lecture 39b on what are called differentials. And I'll tell you what we're going to do today. You know that when you have a function y equals f of x, you sometimes denote its derivative as dy dx. It looks like a fraction, but we've been a little bit evasive about what exactly is this dx and what exactly is this dy. We just look at that as a grouping of symbols that stands for the derivative. Likewise, when we write an integral, we end it with the dx, as if that's a punctuating period. But we haven't really said what is dx. So the goal for today is to give meaning to these entities, dx and dy. What are they? Well, I'll tell you. They are called differentials. And that's our topic for today. We're going to make sense of the notation dy dx. We're going to give a meaning to dy and an explicit meaning to dx so that dy divided by dx equals f prime of x. And here's how it's done. Given a function y equals f of x, we define two variables called dx and dy. So dx is the name of one variable, and dy is the name of a second variable. And we do this as follows. Take the function y equals f of x, and pick an x value, like right here. This dx, we think of that as an increment to x, something that you would add to x. So if dx is positive, you can take x plus dx. It's a little bit to the right of x. So dx is just a variable standing for something you add to x, some quantity. Now in this picture, we're now going to take the tangent line right at the point xf of x, right there, and we're going to make a little triangle whose horizontal side goes from x to x plus dx, and it has a corresponding vertical side. Now that horizontal side has length dx from this picture. So this dx is just the length of that horizontal side. The vertical side of that triangle, we're going to call that dy. So if you think about this picture that we have here, the rise over run of this red tangent line is dy divided by dx in this picture. And that's the slope of that tangent line, which we know as f prime of x. So when dx and dy are defined this way, dy divided by dx equals f prime of x. Now, because dy and dx are numeric quantities, or variables representing numeric quantities, you can multiply both sides of this equation by dx, and you get dy equals f prime of x times dx. So this dy right here, that's what it's equal to. Given a dx, dy is going to be equal to f prime of x times dx. Now it's important to realize in this picture that dx is a variable. It can change. And depending on its value, dy is equal to f prime of x times dx. So in this picture, if you made dx bigger, dy is going to get bigger too. As dx changes, dy is always equal to f prime of this x times dx. Now, usually we think about dx as a pretty small quantity that you're adding to x, and you get a fairly small dy in that case. But really, in this definition, dx could have any value whatsoever, and you get a corresponding dy. So these variables, dx and dy, as defined in this picture, are called differentials. And they are related by this equation. dy is equal to f prime of x times whatever dx is. dy equals f prime of x times dx. Now it's important to realize in this equation that relates dy and dx, there are actually three variables. There's dy and there's dx, but there's also this x right here, which we've kind of regarded as being fixed in this picture, but it could be anywhere in the domain of f. So this equation, again, has three variables. So what's happened here is, on this slide, we've given an actual meaning to dx and an actual meaning to dy in such a way that dy divided by dx equals f prime of x. So this notation matches up. Let's look at an example. Think of the function f of x equals x squared, graphed here. The relationship between the differentials dy and dx for this function are, as defined on the previous slide, dy equals f prime of x times dx. In this case, f of x is x squared, so f prime is 2x. So we get dy equals 2 times x times dx. Again, there are three variables here, dy, x, and dx. And this equation relates all three of them. Let's take a specific value for x, say x equals 1, and plug that in. If x is equal to 1, dy is 2 times 1 times dx. Or simply, dy equals 2 times dx. So this equation says that when x equals 1, dy is always twice dx. And think about that in terms of this picture. 1 is about right here. Go up to the graph at x equals 1 and make that little triangle whose horizontal side is dx and whose vertical side is dy. This equation says that whatever dx is, dy is going to be double that. dy equals 2 times dx. So you can imagine making dx a little bit bigger here. dy is going to get a little bit bigger. It's going to be twice whatever dx is. Let's take another value of x. Just for illustration, let's say x equals minus 2. Well, then dy would be 2 times minus 2 times dx, or dy equals minus 4 times dx. And let's look at that on the picture. Minus 2 is here. You go up to the graph, and you make this triangle with sides dx and dy, and hypotenuse the tangent line. And because that tangent line has negative slope, you can see that dy is going down here, and in fact it is negative 4 times whatever dx is. So you go over a distance of dx and you're going down a distance of dy, which is minus 4 times dx. So these differentials, dy and dx, defined this way, they're just configured so that dy divided by dx equals f prime of x. We've given meaning to these terms so that that actual fraction equals the derivative that we want it to be equal to. But there's more to this than just notation. One really important thing and very useful thing about differentials is that they allow variables to be separated in a sense that I'm going to define here. Think about this equation, dy dx equals f prime of x. We've now given explicit meanings to dy and dx so that that is just a fraction, dy divided by dx. And we can clear the denominator and multiply both sides by dx, and you get dy equals f prime of x times dx. And look at that, all the x's are on one side and the y's are on the other. We've separated the variables here where they were kind of all mixed up in this equation. And you will see, particularly in the next lecture, that separating variables is a really useful thing to be able to do. And differentials allow us to do it. I'd like to give you an historical perspective on how differentials evolved over the years. And if you're not interested in this, you can just fast forward through this slide. and you'll be fine. But I think this is kind of enlightening. Here's our picture of how dy and dx are related. And they're defined in such a way that dy divided by dx equals the derivative f prime of x. And I'm going to write that down here, dy dx equals f prime of x, but allow me to use one of our limit definitions for f prime. Limit as h goes to 0, f of x plus h minus f of x over h. In this limit, h is regarded as a variable that's added to x, and in our picture, that variable is dx. So to make this limit match the picture, we're just going to change that h to dx. We're just changing the variable. That doesn't change the value of the limit. So every time we have an h in this limit, I'm going to change that to a dx. So this matches the picture. So from this limit, you might say that dy dx is approximately equal to f of x plus dx minus f of x over dx when dx is very small, because the limit says that as dx goes to 0, that quotient gets closer and closer to dy dx. Now let's look at the numerator of this fraction, f of x plus dx minus f of x. Where is that in this picture? Well, f of x plus dx is this y value, f of x is that y value, so their difference is the distance from f of x to f of x plus dx. It's this vertical distance here that I've labeled. That difference you can think of as the change in y brought about by a change in x by dx. So you're at x, you added dx to it. What happened to y? It went up by this quantity. So consequently, this f of x plus dx minus f of x, sometimes we call that dy, or delta y, I'm sorry. We call it delta y, not dy, but delta y. So dy is this length, and delta y is this vertical distance, the change in y. So the numerator of this fraction, we're now calling delta y. So let me update that. I'll just make this fraction delta y over dx. So we have dy dx, dy over dx, is approximately equal to delta y over dx when dx is very small. That's what this limit is saying. Well, in this picture, let's make dx small. Let's make it smaller and look at dy and delta y. They're both getting smaller too, but you can see that the smaller dx gets, the closer and closer this ratio dy over dx is to delta y over dx. So dy over dx is very close to delta y over dx when dx is very small. And you might even be tempted to say that dy dx equals delta y over dx when dx is, so to speak, infinitely small, which admittedly doesn't make a whole lot of sense, but there's some kind of logic to it. Dy over dx is equal to the quotient delta y over dx for really, really, really small, infinitely small values of dx. And this is actually how originally derivatives were conceived. Before 1850, dx and dy were viewed as infinitely small quantities. And in fact, dy was even thought of as delta y in this picture. So the derivative was the quotient delta y over dx when dx was infinitely small. And these things were called infinitesimals. This was long before limits were invented, and this was on kind of a shaky logical foundation, and that's one of the reasons limits came on the scene, to make sense of this infinitely small type of quantity called an infinitesimal. And now we have limits. We still retain this notation dy dx because it's a really useful notation as is suggested by this picture. But what we've done today is we've given an actual meaning to dy and dx that makes this quotient exactly equal to f prime of x. And we've avoided the logical inconsistencies or problems of infinitely small quantities. So that's how differentials and derivatives evolved to our modern point of view. I want to say a few concluding remarks about differentials. They have a rich history, but they're also really useful. Take an equation, y equals f of x plus c, a function, and I've highlighted that. And if you take its derivative, dy dx, you just get f prime of x. The plus c disappears. Now think about dy and dx as differentials. As I said earlier, that allows you to separate the variables. You can multiply both sides by dx. So we get dy equals f prime of x dx. And if you look at these two expressions, they're the kinds of things you would stick an integral sign in front of, the integral of f prime of x dx. Now formally, let's just do that. Put an integral on both sides, on the left. So we get the integral of dy equals the integral of f prime of x dx. And what about the integral of dy? What's the function there? Well, there's an implied 1, so that's the integral of 1 dy equals the integral of f prime of x dx. And even if this seems to be going out on a limb, let's just run with it. We could now evaluate these two integrals. The integral of 1 dy, that's a function of y whose derivative is 1. Well, that would be y plus c. On the other side, what about the integral of f prime of x dx? That's a function whose derivative is f prime. Well, that's f of x plus another c. We'll call it c prime. Now add or subtract c from both sides and consolidate into one single constant, and look what you get. Y equals f of x plus c. We got right back to where we started. So what's happening here is you start with a function, you can differentiate it, separate the variables, integrate, and you're back to where you started. The takeaway from this is that if you're looking for a function f of x that satisfies dy dx equals f prime of x, to find that function, you know it would be f of x plus c, but you can separate the variables, integrate both sides, and you've got your function. And in fact, in our next lecture, that's going to be the central idea. We'll talk about what are called differential equations, and we'll be using this. But the real takeaway from this is that this is kind of a mechanism that works automatically. Differentials are so seamlessly woven into the notation that you hardly even have to think about them. You can separate the variables, integrate both sides, and you're going to get a meaningful answer. Their importance will emerge gradually if you continue with calculus, but for now, just be aware of differentials, and the notation will take care of itself. Up next, in lecture 39C, we'll talk about differential equations, which is one place where differentials are extremely important. It's a highly useful subject. So I'll see you then, and goodbye.